Good evening. It's looks like it's February 7th in the evening, about 7 o'clock. I think it's the 7th. Yeah, something like that. Maybe it's the 6th. Anyway, it's just snowed. Temperature is dropping. It's a little bit windy, down to about 0 degrees. And I want to do a test to see how much of the range loss of a Tesla Model S in cold temperatures has to do with the heating. And I figure, well, if I can do just leave the car parked somewhere and just leave the heat on, there's an option to do that in the controls. I could figure out how much loss per unit time there is, and you can subtract that from, say, you're driving a certain speed and how much range loss you'd get. So I'm going to try that here, a little experiment, and we'll see how it goes. So we're going to do what here is here. Actually, it's not simple. We don't have to go through any of the major controls. You can just go here and then go keep climate on. Set that to on, so it will stay on while you're leaving the vehicle, and it'll turn off if the battery gets too low. And that's wise because I don't want that to happen. We'll see. I'll follow the app here and see how long that stays. And now it wants to go back to, well, what it was doing before. So, all right, so hopefully this will work, and I'm going to leave it set to actually something that I would drive with, and that's maybe something like 18 Celsius. Right now it's minus 17 outside. That equates to about +1 Fahrenheit. It'll be dropping below 0 here. Battery is at 62% state of charge. If you're wondering what I'm doing tonight, for the next several hours, I'm going to be grooming cross-country ski trails with this snowmobile here. This is a 1995 Alpine sled. As you can see here, it's got one ski and 2 tracks, so it's a little bit different. Most sleds have 2 skis and 1 track. So there's that one single ski there on the sled. So it's a nice classic sled to be grooming with. We're going to do that for the next several hours, and we've had about 10 inches of snow, so time to groom. And now we're in the Piston Bully. So this is what 10 inches of new snow looks like. And I'll swing around over here. Okay, so it's 2:24 a.m. and it's down to 37%. So we'll use that as a gauge. It's negative 22 Celsius, so that's about 7 or 8 below Fahrenheit. So there we go. There you have it. It's time to go to bed. Okay, so what does this all mean in terms of range loss? Well, I did some calculations and they turn out as following. First thing to do is to figure out how much energy you spent, and in order to do that I had to charge up the battery. By the time I got back home, it was a 32% battery. That's when I started charging, and then it stepped at 78%. So I added 46% of the battery capacity, which turns out the meter on the car said that was 36 kilowatt hours added. And so to take 36 divided by 46%, and I get 0.73 kilowatt hours per percent battery. So how much did I consume during the test? It was starting out at 62%, ended at 37%, so I consumed 25% of the battery capacity, and I multiply that by 0.73 kilowatt hours per percent, and I get 19.6 kilowatt hours. And that happened over a 7.07 hour period for an average power of 2.77 kilowatts. So the next part of the calculation is to figure out what are the reference speed and temperature to define the rated range in the car. So as of February 2019, my rated range was 262 miles or 422 kilometers. Again, from the previous screen, the battery capacity is 78.3 kilowatt hours, and that over 422 kilometers is 186 watt hours per kilometer, or in miles, it's 280 watt-hours per mile. Now, it seems that I get when I'm driving, if the car is using up rated range at approximately 62 miles per hour and a temperature of around 70 degrees, no wind, and flat roads. So that's the reference, and anything we do, add hills, cool down the temperature, is going to increase the power it needs to go through those conditions. So we're using 62 miles per hour as the reference speed. I tend to be somewhere between 62 and 65 to get my rated range, but I'll use 62 miles per hour because it conveniently converts to about 100 kilometers per hour. So at that speed, times 186 watt-hours per kilometer at my rated range, that would mean 18.6 kilowatts is my power output to cruise at 62 miles per hour and 70 degrees Fahrenheit or 21 degrees Celsius. That 21 degrees Celsius will come up again in a few minutes. Now, so some of the effective heating, so what are we going to do with that? 18.6 kilowatts is our reference, and we calculated earlier 2.77 kilowatts is what we use from heating. That ends up being 15% of the driving kilowatt hour range above. And if you add those two together, that's 21.3 kilowatts. And to calculate the loss, it would be 1 minus the rated power divided by the total power, and then you multiply that by 100%. We get 13% loss with that calculation. That doesn't explain the actual loss, which is more like 30%. So what else could be going on? Well, we're also driving through more dense air. The effective density is a function of the outside air temperature, assuming the outside pressure is about the same. So during the test, we had minus 20 degrees Celsius outside, which is also in Kelvin. That's the scale that's more comparable for calculating the density. And 21 degrees Celsius is 70 degrees, which we earlier referenced as the rated range, which is 294 degrees Kelvin. So as density is inversely proportional to the temperature, we just divide 294 by 253 and calculate that we have a 16% increase in density. So it takes 16% more power to move through that air. So 1.16 times 18.6 kilowatts reference power gives us 21.6 kilowatts in the higher density air. So that amounts to a 14% range loss. But there's also other things like wind chill, which we can calculate. Our driving speed is 100 kilometers per hour, and so you look at that on the fancy U.S. National Weather Service wind chill chart I used, and it conveniently turns out that that speed and the temperature of about minus 5 Fahrenheit gives us about right on, minus 40 Fahrenheit, which is also minus 40 Celsius. So that changes the effective outdoor temperature. So indoor, I had the car, inside the car set at 18 degrees. Outside it was minus 20 degrees. Gives us a 38 degree temperature range. But with wind chill, that effectively is minus 40 degrees. Now it's a little bit different between cars, and the wind chill chart was really calculated assuming human skin, but we'll assume things are about the same. So that increases our temperature difference to 58 degrees, and you take that ratio of 58 divided by 38 at 2.77 kilowatts, that gives us that raises our power to 4.22 kilowatts. So in total, we add these all up, we have 18.6 kilowatts for nominal driving at 70 degrees, no wind, and flat roads. So we add 4.2 kilowatts to heat the car because it's cold and windy. We have to add 3 kilowatts to get through the air that's more dense. That gives us 25.8 kilowatts total. So you calculate 1 minus 18.6 divided by 25.8, multiply by 100%, you get 28% loss, and that's a lot closer to reality. Again, there's also probably some rolling resistance and things like that further increase the loss a bit, but with these calculations so far, just to account for environmental conditions, we've come up with pretty close to the rated loss of 30%. Now, that'll occur on trips that are relatively long when the car has had a chance to equilibrate and warm up on the drive. If you take shorter drives, the car will be spending a greater fraction of its energy warming things up, warming the inside from whatever temperature it was when it was sitting outside, and also warming up the battery. And that will make short trips a lot greater in terms of loss. It can be 50% or even more if you're just driving 5 miles or so. So 28% loss is a good reference for what I've had on longer trips, and it certainly can be explained by density and just temperature plus wind. So that's all. Thanks for listening.